In this video, we're going to look at finding features of rational functions, and we're going to do so only by looking at the equation without really having a graph. And the features we're talking about are the domain, any kind of discontinuities along with their types, intercepts, and end behaviors. Now, the domain of a rational function is the set of all real numbers except for any discontinuities that are present. Discontinuities are any values of x that will make the denominator equal to 0. And if I'm looking at this generic problem that I wrote up here, the numbers that make the denominator 0 are x equals a and x equals c. Now notice I have unsimplified here because even though we can cancel out the x minus a's, the x value of a will still make the denominator of the original problem equal 0, so it's listed as a discontinuity. Now, to identify our vertical asymptotes or our holes, a vertical asymptote is a non-removable discontinuity, meaning that algebraically I can't cancel it out and to remove it, which means that the factor of x minus c generates my vertical asymptote in this problem, while the factor x minus a, since I can algebraically cancel it out, is considered removable, which making x minus a be a hole. Now, in terms of x and y intercepts, the x-intercepts are the zeros of my numerator, and they only make my numerator 0, so the factor x minus b in this problem would generate the x-intercept. X minus a, that factor is my hole, so I can't be a hole and an x-intercept at the same time. And lastly, we have the y-intercept. Algebraically, you make all the x's equal 0, and you evaluate for y. Now, as we proceed forward, there's two more things to talk about before we do some examples. And the first is the multiplicity of asymptotes. So knowing the behavior of a function around an asymptote strictly by looking at that factor. And so let's start with this first problem here on the left-hand side. We see the unbounded behavior from the left and from the right around x is equal to 0. So that tells me that we have a vertical asymptote at x is equal to 0. Now, if one side goes down and one side goes up around that vertical asymptote, we say that it has a multiplicity of 1. We don't write multiplicities of 1. We only write multiplicities that are greater than 1. So if left and right sides go opposite directions, the vertical asymptote has a multiplicity of 1, which means that factor is present in the denominator only one time. So an example of this function would be 1 over x. Now, looking at the next one, we have the vertical asymptote at x is equal to 0. And that vertical asymptote there, notice how the right and left side, so the left side increases without bound, the right-hand side does the same thing. Since they both point the same direction, that's indicative of a multiplicity of 2, and which means that that factor that generated that vertical asymptote would be squared. And so I have here, right here beside it, an example of a graph that has both of these going on. And so look at this graph, and we're just finding the vertical asymptotes and their multiplicities. And so I have two vertical asymptotes with the unbounded behavior. I got x is equal to -1. Notice how one side goes down, one side goes up. That means it's a multiplicity of 1. And at x is equal to 2, both left sides and right sides point the same direction. It means multiplicity of 2. And in terms of writing that equation, our denominator, now I don't have a scale factor or anything, but my denominator here would be x plus 1 and then x minus 2 squared. So that kind of gives you an idea of how we go about writing it. Now let's look at the end behavior model for rational functions. The end behavior model for rational functions is based upon the degrees of the numerator and denominator. So let's say I have a rational function where the largest exponent value of n, or largest exponent value of x in the numerator is n, and the largest exponent value of the denominator is m. And so our end behavior model strictly compares the sizes of the exponents between the top and the bottom. If the degree of the denominator is larger, all right, a lot of people like to think of that as being bottom heavy. That means the denominator grows faster than the numerator does, meaning that there will always be a horizontal asymptote of y equals 0. So horizontal asymptote, y equals 0. Now, if the numerator and denominator are of the same degree, so n is equal to m, an example of this would be like 2x squared over x squared minus 1. So the largest exponents here are both 2's. The end behavior is going to be the ratio of the coefficients, and that's a horizontal asymptote. So horizontal asymptote, it's the ratio of the coefficients. So I'm getting this from my generic problem I have here. So it'd be y equals a over b, which means that my little example I wrote here would be y equals 2. And lastly, the last case scenario would be if the degree of the numerator is larger than the denominator. We call this being top heavy, and there is no horizontal asymptote if this happens. And so if we want to get the end behavior, we'd actually have to do long division. So we'll do long division for end behavior asymptote. So let's do some examples here. All right, so I want to analyze and I want to sketch the following rational functions. We're going to work through these things one at a time. Now, when I'm given a rational function, I want to analyze it and or sketch it without having a calculator or a graph. The first thing I would recommend doing is factoring. So we're going to rewrite this problem. We're going to factor the whole thing. And so what we have is we'd have x minus 1 over the denominator will factor to x minus 2 times x minus 1. And so we'll work our way through trying to have this whole list of analysis things and to fill out. So once you have it factored, figure out the x values that make the denominator 0. The x values that make the denominator 0 have to be excluded from my domain, so that means x cannot equal 2 and x cannot equal 1. Those are my discontinuities, so I'm going to write those x values as my discontinuities, and it will classify their types of discontinuities in a moment. So the domain is the set of all real numbers except for the discontinuity. So negative infinity until I get to the first discontinuity, and then the first discontinuity to the second, and then the second discontinuity to positive infinity. So my domain, done. Now, identifying the kinds of discontinuities. So our kinds of discontinuities we identify based upon if we can remove them or not. So when I'm looking at my problem, notice how I can eliminate the factor of x minus 1, which means that the x equals 1 discontinuity is a hole. So I have a hole at x equals 1. Now, we'll get the y value of that hole in just a minute. Notice how we could not cancel out the factor of x minus 2. Since it was not removable, that is a vertical asymptote. So to get the x or the y value of the whole, we're going to take our simplified problem. Notice how I already had canceled out the x minus 1s here. And we're going to rewrite our simplified form. So we have y equals 1 over x minus 2. And then we're going to put in the x value of our whole into our simplified problem. And we're going to solve for y. So y would equal 1 over 1 minus 2, which gives us negative 1. So the y value of the whole is at negative 1. Right? Vertical asymptote we already identified. We have vertical asymptote at x is equal to 2. And we want to describe the behavior of the function around that x value using limits. Well, I save all the behavior, end behavior, and that the behavior around an asymptote for the very end, because after I get my graph to kind of help me. Now let's talk about intercepts. So Xintercept. Xintercepts are the values of x that make the numerator equal 0. Well, if I look at my factored form, all right, I had x minus 1 up there as a factor, but that was the factor of the whole, which means that after I reduced it, and I was left with 1 over x minus 2. There is no x value that can zero out this numerator or zero out the whole value of the function, which means that we have no x-intercepts. So there are no x-intercepts. My y-intercept, on the other hand, what we do is we take our problem and we're going to put in 0 for all of our x's. So everywhere there's an x, I'm going to put in a 0. So I got 0 minus 1 in my numerator. And in my denominator, we have 0 minus 0 plus 2. So our y value here is negative 1/2. So we have a y-intercept of 0, negative 1/2. Okay, and now we have, lastly, our end behavior. So in behavior, let's go look at our degrees. So I'm going to my original problem. Biggest exponent in the numerator is 1. Biggest exponent in the denominator is 2. This is bottom heavy. Bottom heavy rational functions will have an end behavior is a horizontal asymptote of y equals 0. Now, we've been practicing all up to this point by writing end behavior using limits. So that would be the limit as x approaches negative infinity for this function of x is going to equal that horizontal asymptote of 0. And the limit as x approaches positive infinity for this equation is also going to approach that horizontal asymptote of 0. So let's try to make a sketch with all these characteristics. So real rough sketch. Make a y-axis. Make me a x-axis here. And we don't have any x-intercepts to worry about, but I'm going to make my vertical asymptote at 2. So vertical asymptote, make a dashed vertical line. All right, we do have a y-intercept. We have a y-intercept of negative 1/2. So I'll put a dot kind of like somewhere in there. And that's about all we have to work with. So we have to figure out, okay, well, how's the graph going to behave? Well, I have a defined point here. I know that as I head off to the left, I have to be approaching the x-axis, but I can't cross it because I have that end behavior asymptote that is the x-axis here. So I have to work towards the x-axis on the ends. So the left side here is going to approach the x-axis and never actually quite get to it. Now, as to the right side of that point, right, I know I can't go up because if I went up to increase without bound, I'd have to cross the x-axis. We don't have an x-intercept over here. So it's going to have to work towards the vertical asymptote and show unbounded behavior in the negative direction. So I'm going to decrease without bound. So there's that side, which means that I can go write that behavior around that vertical asymptote. So as we approach 2 from the left-hand side, we're going to be decreasing without bound. So this is kind of a new part for us. We haven't done this yet in class. So we want to describe the behavior using limits. So we're going to use one-sided limits to do this. So we'll say the limit as x approaches 2 from the left-hand side for this function of x. It is decreasing without bound, heading towards negative infinity. So we're going to say that's what the limit equals. It's describing the function's behavior. Now we have to do the right-hand side. Now, the right-hand side, we have to either put our graph up here or down below the x-axis. Now, either way, I can't cross the x-axis because I don't have any x-intercepts. To figure out where it has to go, we pay attention to the multiplicity of the asymptote. If I were to put it beneath the x-axis and make it decrease without bound, the multiplicity of this vertical asymptote would have to be 2. But it is not 2 because in factored form, it is not squared. It just is a multiplicity of 1, which means that left and right sides have to point opposite directions. So that means as it comes at that vertical asymptote from the right, it has to be increasing without bound. So describing that behavior with limits would be the limit as x approaches 2 from the right-hand side. This function of x is going to be increasing without bound. So I say equals positive infinity. Let's look at this second one. So same rule applies. If I want to do an analysis or find my domain or anything else, it's best to factor the problem and get a better look at it. So I'm going to pull out the GCF of negative 2 in the numerator. That's going to leave me with x plus 1 in my numerator, and in my denominator is still x minus 4. So now that I look at this thing in factored form, there's only one number of x that makes the denominator equal to 0, and that's 4. So x cannot equal 4, which means that x equals 4 is a discontinuity, so I might as well go ahead and write that. The domain of rational functions is the set of all real numbers except for the numbers that make the bottom 0. So in this case, it would be negative infinity to the one discontinuity of 4, and then from 4 to infinity. So I eliminated that one number from my domain. Now we need to classify, well, what kind of discontinuity is this? Well, the factor x minus 4 cannot be canceled out with the numerator. So since it can't be canceled out, this is considered non-removable. A non-removable discontinuity for rational functions are vertical asymptotes. So that is a vertical asymptote, which means since that was the only discontinuity, this problem does not have a hole. So there are no holes. So x equals 4 is my vertical asymptote. And we're going to save the behavior around that vertical asymptote with limits. And we're going to find our intercepts. So the intercepts, start with the x-intercept. So the x-intercept is what makes the top equal 0 and only the top. Well, I have this factor x plus 1 up here, which means that if I put negative 1 in for x, it would zero out my numerator and leave my denominator with negative 5. 0 divided by negative 5 is 0. So my x-intercept is negative 1. So my x-intercept is at negative 1, 0. My y-intercept, on the other hand, what you do is you put in 0 for all of your x's. So I put in 0 here, and I put in 0 there, and I do that, I'm left with negative 2 over negative 4, which gives me a y-intercept of 1/2. Okay? Now we're talking about our end behavior. So the end behavior rational functions, you're looking at our end behavior model. We compared degrees. So biggest exponent of the numerator is at x to the 1 power. Biggest exponent for x in the denominator is at x to the 1 power. So they are the same degree. So same degree. So my end behavior is going to be the ratio of the coefficients. So it would be negative 2 over 1, which means that I have a horizontal asymptote at y equals negative 2. So my end behavior is the horizontal asymptote of y equals negative 2. And we can write this behavior using limits. So the limit as x heads towards the ends of its domain, which would be either negative infinity or positive infinity, this function is going to be approaching a value of negative 2. So now we're ready to start sketching this. So let's make a coordinate axis and start trying to get information on here. All right, so I got x and y. Let's start with our vertical asymptotes at 4. So I got a vertical asymptote of 4. 1, 2, 3, 4, 5, 6. Vertical asymptote goes at 4. All right. Now, we got the vertical asymptote in there. Let's do our intercepts. I got 1 at negative 1. All right, and I have a y-intercept at positive 1/2. So I got 2 dots there. We have a horizontal asymptote at y equals negative 2. So let me make a end behavior asymptote line of negative 2. And we're ready to start sketching. So start with the defined points that you have. So I have these 2 points right here. I know the function has to pass through those 2 points. Now, as I work from the x-intercept and go to the left, I have to make this function go towards the end behavior asymptote. So I can get that part. So it has to do this. Now, as I work my way from the y-intercept to the right, I know the function cannot go down. And it's not because the horizontal asymptote here. The horizontal asymptote is strictly for the end behavior part of the graph. The middle part of the graph can actually cross the horizontal asymptote from time to time. However, the reason why I know it doesn't go down is because there exists no x-intercepts in this area here. So the only place for it to go to show its unbounded behavior is to increase. So it's going to be increasing without bound as it heads towards that vertical asymptote. Now I have the right side of the picture to do. Well, there's only one place to put the graph, so that way it doesn't have any x-intercepts over here. That's going to be down here at the bottom, in between the end behavior asymptote line and the vertical asymptote. So it would have to go down here. Now let's write the behavior of the function around its vertical asymptotes. So what we're going to do is we're going to write the limit as x approaches 4 from the left and from the right. So the limit as x approaches 4 from the left-hand side, the graph is increasing without bounds. It's going to keep going up. So we would write this behavior as the limit as x approaches 4. Now we use a directional indicator from the left side, superscript or a little negative sign behind it. For this function of x, it is increasing without bounds, so we'll say equals positive infinity. And then the right-hand side, we look at the right-hand side. As we come at 4 from the right-hand side, we're going to go down. So it's decreasing without bound. So we write this as the limit as x approaches 4 from the right-hand side. So directional indicator is going to be the plus sign. This function of x is decreasing without bounds, so we'll say head towards negative infinity. All right, one more example here. All right, we have this rational function like we've done for all the other ones. Let's factor this problem completely so that way we can look and see what we have. Well, if I work to start factoring, I have a common factor of x in my numerator. And if I pull out x, it's going to leave me with x squared minus 16, which is a difference of squares. So I can say x minus 4 times x plus 4 there. My denominator, I have a common factor of 2. Pull the 2 out, that's going to leave me with x squared minus 9. That's a difference of squares to make x minus 3 times x plus 3. So now we identify the numbers we cannot use for x. You cannot use values for x that create division by 0. So x cannot equal negative 3 and x cannot equal positive 3 for that reason. Those two numbers are your discontinuities. So I'm going to go ahead and write those as x equals 3 and x equals negative 3 as my discontinuities. My domain for this rational function is going to be the set of all real numbers except for my discontinuities. So it would go from negative infinity to the first discontinuity of negative 3, and then from negative 3 to the second discontinuity of positive 3, and then from positive 3 to infinity because there's no more breaks in the domain from there. Now let's identify the kind of discontinuities we have. Well, we look at our problem in factored form. The two numbers that made the denominator 0, those factors cannot be removed. I can't cancel them out with anything in my numerator, which means they are non-removable, meaning they are both vertical asymptotes. Since they are both vertical asymptotes and there are no more numbers of x that will make the denominator 0, there cannot be any holes. So I'm going to write none for my holes. We've already established that we have vertical asymptotes at x equals negative 3 and x equals positive 3. And we'll describe the behavior of the function with limits at the very end. So the next thing we have are intercepts. Our x-intercepts are going to be the values for x that make the overall function equal 0. And when it's in factored form, they are the numbers of x that make only the top equal 0. We have three numbers that will make only the top equal 0. Negative 4, positive 4, and 0. So we have three x-intercepts here. We have an x-intercept of 0, so 0, 0. An x-intercept of negative 4, 0. And an x-intercept of positive 4, 0. Now, my y-intercept, since I have the origin as an x-intercept, that's also going to be my y-intercept. A function, hence the word function, cannot have more than one y-intercept because it would fail the vertical line test. Okay? In behaviors next. So let's go look at and compare the degrees of our function. So when I look at my degrees, I look at an unfactored form. I have degree 3 in the numerator, degree 2 in the denominator. This is top heavy, which means as you start increasing, or you actually start increasing without bound or decreasing without bound, the numerator is going to be growing larger than the denominator. So to get our int behavior here, we are going to do long division. We got a long divide. Long divide the bottom into the top. So what we have, I already forgot the problem, is 2x squared minus 18. 2x squared minus 18. Well, I'm going to write 0x minus 18. It's got to divide into my numerator, which is x to the third minus 16x. So x to the third plus 0x squared minus 16x. That's supposed to be a 3, not a 2. All right, and then I have the number 0 right there. So I want to do that long division. So I figured out how to make the 2x squared become x cubed. You do that by multiplying by 1/2 x. Multiply everything by 1/2 x. That's going to give me x to the third. And then I got 0x squared. And we have minus 9x. We subtract. And that gives us the x to the thirds cancel. There are no x squares. Negative 16 minus negative 9 gives me negative 7x. That is my remainder. So, and I can't keep going because the degree of what I have is less than the degree of what I'm dividing by. So what we did when we did that long division is we rewrote our rational function as 1/2 x plus negative 7x over 2x squared minus 18. This piece, which represents the remainder, is going to, as x increases or decreases without bound, is going to approach a value of 0. So I don't worry about the remainder. The end behavior, instead, is the part that is up here on the top of our quotient, which in this case is going to be 1/2 x. So our end behavior asymptote is going to be the slanted line y equals 1/2 x. Now we think about what the line y equals 1/2 x is. It has positive slope, which means that right side goes up, left side goes down. So I could actually go ahead and write this end behavior limit. So the limit as x approaches infinity, so I go way off to the right, this function of x is going to be headed upward, so it's going to head towards positive infinity. The left side here, the limit as x heads towards negative infinity for this function of x, much like that line that we have, the left side goes down, is going to be headed towards negative infinity. Okay, so let's start putting all this together in our graph. Make a set of coordinate axes here. All right, where are our intercepts? Negative 4 and 4. I'm just going to go 7 by 7. All right, when I graph, I start with all my asymptotes. So let's go with the vertical asymptotes at 3 and negative 3. So vertical asymptote at negative 3 and positive 3. We have intercepts at the origin, negative 4 and positive 4. So origin, negative 4, positive 4. And then we have this slanted asymptote. Y equals 1/2 x. I'm going to put it in red because that was the equation that I did it in here. So this is my end behavior asymptote. So that line goes through the origin, has a slope of 1/2, so it goes up 1 over 2, up 1 over 2, up 1 over 2, and I'm just going to continue that pattern to give me some dots to connect until I kind of start running out of room. All right, and then I'm going to connect my dots here with a little dashed line, try to keep it going. So this is what the ends of the graph are going to head towards. All right, so now let's put all this together. So my function here, I have the x-intercept at -4. So I know my graph's going to go through that point, and it can't cross the vertical asymptote. So I got to figure out which way is it going to go. Well, my options are down or up. Well, since my graph as I go to the left has to head towards my end behavior asymptote, I'm going to go this way. And the multiplicity of this x-intercept is 1, so it has to pass through it and head on the other side, so that means that this side goes up here. Now, what that also tells me is since the multiplicity of my vertical asymptote was 1 because it wasn't squared, is that at this x-intercept is 0, when I head to the left back towards that vertical asymptote of -3, that I cannot go up, I have to go down. So it's going to go this way on the way down. So while we're at this stage, let's go ahead and describe that behavior of the function using limits as we approach x equals 3 from the left and the right. As we come at 3 from the left, my graph increases without bound, and as I come at 3 from the right, my graph decreases without bound. So we're going to illustrate that using limits. So the limit as x approaches -3 from the left, our function was increasing without bound, so we'll say equals infinity. And as we approached -3 from the right, our function was decreasing without bound, so we'll say equals -infinity with that limit. So that's the behavior around -3. We got to do the same thing for +3. So let me go ahead and pre-make my two one-sided limits. So as I come at 3 from the left, the directional indicator, the minus sign behind it, and as I come at 3 from the right-hand side, directional indicator behind it with the plus. So let's go back to our graph. So we're right here. We made it all the way to the origin, and I have to keep going to the right. So my options are go down or go up. Well, since I'm at this x-intercept, and this x-intercept has a multiplicity of 1, I cannot go down. It has to pass through it. And so since it has to pass through it because of that multiplicity of 1, this side's going up. Likewise, when I'm at my x-intercept at 4, I know that I cannot work back towards the vertical asymptote and go up because the vertical asymptote does not have a multiplicity of 2, which means that both of these sides cannot point the same direction. They got to go opposite directions. So from this vertical asymptote back, or this x-intercept back towards the vertical asymptote has to go down. And then when I get through the x-intercept, it has to approach that end behavior slanted asymptote that we have illustrated there. So we can finally write this last limit here, describing the behavior as we approach 4 from either side. So from the left side, graph goes up, which means equals +infinity. And as we approach that x value from the right, graph goes down, which means -infinity.